Okay, let me welcome you back to the this second part of this morning session. The next speaker is Professor Eli Jablonovich. He's going to talk about tunnel transistor mechanism based on density of state switching. Eli, as all of you know, is the director of the E3S Center, who is the major coordinator for this symposium, and he's had a long and illustrious career in solid-state devices. And I will not. It would take me a good part of his presentation time to go through all of his accomplishments, so I will not do that. And I will just invite him here to the podium.
Okay, very good. Thank you very much. Yes, I appreciate not being embarrassed. Okay, well, we just heard a very exciting presentation with some important breakthrough results showing that the tunneling mechanism could be very interesting and very exciting as a new and more sensitive type of switch. But there are still many fundamental science aspects to be analyzed. And I'll try to get into those to try to figure out how we can really fulfill every requirement that needs to be satisfied. So it came up already in the presentation by Wilfred Hensch and in the discussion period that it is necessary to fulfill three requirements before we could declare success and have a new and more sensitive and lower voltage switch. And the first, of course, you have to reach better than 60 millivolts per decade, and I would argue it might even be possible someday to even reach 1 millivolt per decade. So one of the things that bothers me is that, well, maybe it's correct to be looking just for the next generation, but we'd like to know that it's a very good path and it leads to a whole roadmap that might eventually get us down to a millivolt per decade. That would be very nice. The other requirement that we heard from Professor Iladalon is that almost irrespective of the device or the conditions, you always need a very good on-off ratio. So that becomes very important. So we need a steep switch. This is steepness. We need good on-off ratio. And we need current density, except that I think it came up in my question. I said, well, shouldn't the current density be conductance density? Because a milliamp per micron, if you're operating at really low voltage, you just need to have a millimole per micron. And so at lower voltage, you can all the performance is the same as long as you have the corresponding on-state conductance. And this is really a requirement for density or miniaturization or economics, that we have to have enough conductance to drive the wires. So I put a very big emphasis on driving the wires, which already we heard from the first two speakers. So how to achieve these three specifications? And you know, it's not enough to achieve one. We all know that. To have something that's useful, we have to achieve all three. And so already the controversy arose. What is the mechanism by which we can achieve this switching action? And so one of the mechanisms, that I think the dominant mechanism in most devices, most TFETs up until now, is to modulate the tunnel barrier thickness. So you can imagine that you have to tunnel that entire distance, and if you put on a reverse voltage or some gate voltage, you could make the distance shorter, and that has a very pronounced effect on the tunneling probability. But it is steep. It is particularly steep at low current densities, and if you manage to get it up to high current densities, which you can by making this thickness very narrow, then there's a tendency to lose steepness. On the other hand, there's another mechanism that we need to recognize, and that's the density of state switching mechanism. And the second mechanism says, look, it's very thin. You've one way or another, you made the barrier very, very thin. But your switching action is not coming from modulating the tunneling probability, but it's coming from aligning the conduction and valence band. So if you imagine that the conduction band were up here, then you would have no states to tunnel to. And then you lower the conduction band, and you have perfect alignment. And let me draw it perfectly if I can. And once you have that perfect alignment, the conductance switches on. And in the way we teach students, we teach students that the band edges are perfectly sharp. But in reality, they're not. But if they were perfectly sharp, this would be a fantastic switch, because the very slightest overlap between conduction and valence bands would turn on the conductivity. Now, it seems to be the preferred mode of operation. It lends itself to high currents, and it keeps a good self-threshold slope all the way up to the high conductance state. But the problem is there's an element of science that has not been studied that we need to study, and that's going to be the point of my talk, is we need to do the science to determine how sharp band edges are. As I say, we teach students, us professors, we teach students that the band edges are perfectly sharp, and they're not, but we haven't really studied how sharp they are, and so we don't really know what performance is possible in a TFET. And so that has to be dealt with. So let me contrast these mechanisms. Suppose you have a Zener diode. Of course, it behaves like a pretty ordinary diode in the forward direction. And in the reverse direction, very famously, it starts conducting, and this is used for voltage regulator diodes and is part of the breakdown mechanism of ordinary diodes in the reverse direction. But that's not necessarily a very useful switch, because it occurs at a substantial reverse bias. On the other hand, there's another type of diode, which is very famous, the Esaki diode. And in the Esaki diode, you are actually running the current backwards. You have to dope very heavily in the Esaki diode. So you dope heavily. Part of the heavy doping is to make the tunneling distance very short, so you have a very thin depletion length, so you can get through very, very easily. And then we're using the density of state switching mechanism, because at exactly this point where the two bands are just lining up, what you get is you go in the forward direction, so you raise the conduction band, and now there's no place for the current to go. So it goes up, and then it says, whoops, I'm no longer aligned with the valence band, and there is no more current flow. So this very famous negative resistance step is actually the density of states switching mechanism, and it relies upon how sharp the edges are. However, in real Esaki diodes, they never really learn how sharp the band edge is. Of course, it's great that you have a negative resistance region, but both sides are very heavily doped, and when it's heavily doped, we know we're not going to get very sharp band edges, and many other problems are associated with the doping, and so we get what we get. It's not bad. You have your negative resistance region, but it doesn't really reveal how well it's possible to perform. Now, I should mention that when it's down here, when it's biased in reverse, then there's no problem. The current flows, and in fact, it flows low resistance in the forward direction, low resistance in the reverse direction, both. So that's the Esaki diode. Now, what I'd like to draw your attention to is that the type of diode we are more interested in is more similar to the backward diode. And in the backward diode, you don't have such heavy doping. And in fact, you dope it relatively lightly, so that, but enough so that the two band edges are perfectly aligned at zero bias. And so the negative resistance step that occurs at forward bias for the Esaki diode would occur at zero bias for the backward diode. And so this exact step in reverse is exactly the density of states switching action, and it's very analogous to the Esaki diode, except it's in the reverse direction, and you can adjust it. It can turn on at a according to the doping. You can adjust the Fermi levels in such a way that the turn on could be at up to, let's say, 1/10 of a volt in reverse. So the backward diode has been known since the 1960s and have traditionally been made in germanium homojunctions. And they're actually a better diode because you see how sharp the diode is in the forward direction. Because of tunneling, it's actually sharper in the reverse direction. So it actually works better as a backward diode. That's the reason for the name, backward diode. And I see some puzzled looks, but this is certainly worth thinking about. It's going to be one of the main points in this presentation. So what we want actually, we want TFET, we want the gate to actuate the backward diode so you get this perfect alignment. And that would be very ideal. But in the meantime, it might be useful to think about the two-terminal devices. And the great example came from the very beautiful work from HRL Laboratories 11 years ago, and led by Joe Schulman, who's here in the audience. And he noticed that all of these problems with having a very good tunneling probability can be resolved in what's called the type 3 band alignment. Now I forget now, is this staggered or not staggered, but basically you have a perfect alignment between the valence band in gallium antimonide and the conduction band in indium arsenide. And in all of nature, this seems to be the only good example we have. There are a couple of others that might work as well, but it's extremely rare to get this type of band alignment. But you see what happens with this type of band alignment. We have a very thin barrier region, so we can get the very high current densities that were given us by Alan Seebaugh. And so you don't need the heavy doping, and you get the band alignment, and it could be very instructive to study these. Of course, these have been very extensively studied, and the aim was more toward nonlinear radio mixers and a little bit less toward switching. But now we see that this work is really a precursor of the tunnel FET. It's the two-terminal version of the tunnel FET. And if you ask what is the ideal switching principle, if you're truly using density of state switching, you can imagine you having a quantum well, let's say in the valence band, and having a similar quantum well in the conduction band, and your current will flow because they're perfectly aligned, and that's the on state of the TFET. However, if you misalign it like that, in principle, you could have, the electrons in the valence band would go, but then they have no place to go. So this is the ideal switching mechanism for the density of state switching. But as I say, there's still some controversy whether it's tunnel barrier modulation or density of state switching. It's still very much in question. So let me tell you some of the strange things that happen when you try to get perfect energy alignment. You want to make a switch with perfect energy alignment. So the two energy levels, you say, I get them perfectly aligned, but then what happens in quantum mechanics, energy levels repel each other. And so try as you might to align them, they will actually repel each other. You'd like them to cross, and this is with respect to a gate voltage, and then have the on-state threshold right there. But that's not what quantum mechanics says happens. Quantum mechanics says the two levels will repel each other. And so this is one of the problems we're going to have to deal with. So it's one of the many things that can go wrong. And of course, up until now, things are going wrong, and we have to knock them down one at a time. And I think one of the things you saw in the Seebaugh presentation, the current density has definitely reached the interesting levels. But if you're using density state switching, you've got to be careful with the quantum mechanical repulsion. Second problem that could go wrong. You're trying to make contact, let's say, to some quantum dot structure, and you make contact, let's say, with a resistor, but just because electrons are able to flow out of the quantum dot, immediately the level is broadened. And so you never get perfectly sharp levels, because a perfectly sharp level means you have no contact. and you'll have tremendous series resistance. So you need to do something about the contact, but there are some conflicting requirements, and there's a compromise has to be accepted, and that is the contact conductance that we're trying to achieve has to be balanced against the steep response that we're hoping to achieve. If the levels are perfectly sharp, that means you have no electrical contact, and so you have to be willing to accept a compromise. Now, the quantum mechanical level repulsion problem can be solved by effectively broadening these levels with the contact conductance. And so as you broaden the levels, you prevent this avoided crossing. And so you can think of these levels as being somewhat broadened, and then you can avoid your avoided crossing, and also you provide the conductivity. So that problem can be dealt with. However, it puts some requirements on it. You have your contact, let's say it's a quantum mechanical tunneling resistor, and what you need to make sure is that the transmissivity of the contacts is greater than the transmissivity at the center of the device itself. So this is very paradoxical. That says that if your quantum mechanical coupling is too strong and you get too much tunneling, then you're actually in trouble, because you'll start, the levels will repel each other. And so it says that best of all is to have a device tunneling probability neither too big nor too small. Of course, up until now, it's always been too small, but there is a danger that it could also become too big. And I should mention, around 2% tunneling transmission seems to give you a very good performance. So that's rather interesting. And then the other problems that come up, I could go on and on. We have broadening due to phonons. I'm not even going to talk about defects, but also broadening due to Coulomb blockade. In very small devices, you have that. And because of the phonons, you develop band tails, you get phonon-assisted tunneling. And so you have a situation where you wanted to get a sharp energy level or band edge, but in fact, it's significantly broadened by these. And the trouble with this is we have no idea what the real broadening of band edge is. So I say it's an embarrassment to the scientific world that we don't know how sharp band edges are. Experimental data are almost non-existent, and so the science has to be developed. And as we heard from CBA, this leads then to very nice devices where you have, let's say, an indium arsenide quantum well, and you modulate it with a gate, and you can move the quantum well up and down. And so he already told you that if the density of state switching mechanism is the one that is most important, then there will come a certain point where the band edge of the indium arsenide is just aligned with the band edge of the gallium antimonide, and then you'll get the switching action. If you go any further, the electrons have no place to go, and whereas here you have the on state. So we already saw that. That's the mechanism we hope for, but we don't know for certain if we have it. Now, once you accept the idea that the density of states matters, and maybe we want a step function of the density of states, well, density of states is very strongly affected by dimensionality. And it means that whenever we have a p-n junction, it's not enough to say that we have P and N. We have to say what is the dimensionality on the P side and on the N side. And up until now, most of the time when we mean a p-n junction, we mean one of these where it's three-dimensional on both sides. But there are many types of p-n junctions, and my student created this figure. He counts 9 different types of p-n junctions with different dimensionalities. And for example, the one that Seabaugh showed you and I just showed you is 2D to 3D. You have a quantum well sitting more on a bulk gallium antimonide region. But you have all these other strange dimensionalities. This would be more like a carbon nanotube, 1D to 1D. You could do 0D to 0D. Each of these is very interesting, but they all have a different density of states, and because they have a different density of states, they have a different expected IV curve. So we have to be aware of the ideal IV curves that might arise. And so I'll show you quickly what you get. You know, the 3D to 3D case is not very promising because it looks like even with sharp band edges, the density of state says it only turns on quadratically. So it doesn't turn on that rapidly. This is not bad. This is the structure that Seabaugh showed you. It looks like it's capable of a linear ramp turn-on. The same with the 1D to 1D. The carbon nanotube also is capable of a linear ramp turn-on above threshold. These are rather interesting structures because they seem to have the sharpest turn-on. Obviously, if you have quantum dots, then you just align the discrete energy levels. And interestingly, if you have 2D to 2D, it seems to have a very ideal property. It has a step function in the characteristic. Of course, the step function is just looking at density of states. It's not taking into account that we might have some broadening. And you have some of these other cases as well with different properties, and they all have different issues. The current drive capability is quite good if you look at these. This is essentially one-dimensional, so this is actually very reasonable. This is microsiemens, but that's only for a single channel. If you had an array, you'd get much better performance. And indeed, this is the expected performance in some of the other geometries, and it shows you the step function in the 2D to 2D, and the others also work, but it requires quite a bit more voltage to reach the potential current. But you see here, the millisiemens per micron, you can translate that into milliamps per micron if you're operating at 1 volt. Of course, we want to operate at lower volts, and so the millisiemens per micron, I argue, is a better figure of merit. And for all of these, we assumed about 2% transmission in the main tunnel barrier, because I said we are not allowed to have too good a tunneling transmission. But nonetheless, it's really not bad. It fulfills the requirement of better than 1/3 of CMOS. So this is now maybe 2/3 of what CMOS could do, at least 2/3 of a milliamp per micron. So it looks very good, but it does, to get the really sharp performance, we have to pay close attention to the dimensionality of the p-n junction, and we have not been paying too much attention to that up until now. So there's a whole zoology of all of these different geometries, and so we have actually a preprint on this. You can look this up, but let me summarize with what are the key scientific questions, and that is fundamental band edge abruptness. It's poorly understood scientifically, and we need to understand it. And of course, it would be great if we could have more examples of type 3 band alignments. And then we have to worry about dimensionality and how do we guarantee reproducible thresholds. So these are all issues. But I'm going to close with one final experiment I wish someone would be successful at. And it's the following. We have seen that if we go in the forward direction, of course, we have the Esaki diode. And so we get that sharp behavior. Now, but we don't really want to make Esaki diodes. What we really want to make is more of a backward diode where the switching action occurs at a slight reverse bias. And what I would be happy with, and what has never been seen, is for this step, this forward step in the Esaki diode, to also see at slightly lighter doping, to see a step at reverse bias. Nobody has ever seen that step. And if that step or glitch would be seen, then it would provide spectroscopic information about how sharp the band edges are, because that step in reverse bias would actually be the alignment of the bands. So I think a very, very important experiment just to gather the basic scientific information is to look for the Esaki step, but to look for it in reverse bias where it's never been seen. So let me put that out there as a challenge for the different communities and fields here. And I'll stop for questions. Thank you.
Okay, questions? Yeah.
So the assumption for these models is you're starting with the material with a parabolic band structure.
Actually, wait for the microphone.
Sorry. Yeah. So the assumption in the models was you're starting with a parabolic energy dispersion. Now, how well we know that most natural materials do have that, but then there are materials like graphene or metallic tubes which buck that trend. So if you take that off the picture again, I mean, how does this picture change? Does 2D to 2D still remain kind of the sharpest slope?
One of the things we require is to have a band gap. So some of the systems you mentioned, like the graphene, don't have a band gap, so would not be appropriate. And graphene has the most unusual band structure. But as you mentioned, most of the other things have a finite band gap, and then you tend to have the parabolic band structure. But if you're not satisfied with that, you can repeat these calculations for whatever dispersion relation that you prefer. And it's a kind of a useful exercise to do that. So I encourage you to give that a try.
And one more short question. So again, the other assumption here is your valence band. Another thing that I guess would be interesting to exploit is something that you did for lasers, which is try to make the band symmetric, so that you don't have only one Fermi circle going to another Fermi circle, but you have an entire, macroscopic tunneling rather than just a few electrons.
Right. So I think you're pointing out the effective mass is also very important. And of course, I completely agree. And notice the way I plotted I gave you the shape, but I didn't give you the prefactor, which would contain the effective mass. So it's quite interesting. It means all the ideas of density of states that we're accustomed to in dealing with, let's say, optical transitions in quantum wells, we can apply that same thing to this problem. But it's all similar but slightly different. And that is, you get different functional forms because the problem is slightly different than making, let's say, an optical transition in a quantum well where you're also going from a valence band to a conduction band. And here, the TFET, also we go from the valence band to the conduction band. But we have to take each dimensionality into account separately.
Joe?
I just want to give her some exercise.
Yeah.
I don't have a question. Should there be a step in the backwards direction there with the Fermi levels in the band gap? In other words, not degenerate?
Well, in the band gap, there should be a step in the backward direction. And the way to think about this is that this is a very good example. If you were at zero bias, then the Fermi levels would be aligned. Okay, and if they're aligned, then that means the band edges would not be aligned. So you can see, according to that distance, that's how far in reverse bias you have to go in order to get the perfect alignment. And the way I drew this is you have perfect alignment. So it actually doesn't quite match this figure. This figure would have been at zero bias. It more matches this kind of situation where you look for a step in the reverse direction. And we've reviewed a lot of old data in homojunctions. We've never seen that step in the reverse direction. And I think it would be great for this field if we could find it.
So it's not linear, it's an actual step.
Yeah, there's a step. It's completely analogous to the step that gives you negative resistance in the Esaki diode, because that's the point at which the band edges line up. But it's very hard to see because you have all the parallel paths, you have thermionic current, you have many other things. And of course, the biggest problem is that the barriers have been too thick when you have just depletion. And that's why we have great hopes for the structure that you introduced, which is the indium arsenide gallium antimonide backward diode. There we can have, as Seabaugh showed, we can have tremendous on-state conductivity, and we have a chance of seeing that backward step. But I would say that's sort of an indication that we're going in the right direction if we ever see it. And if anyone here in the audience, they already have been surprised that many people have already done many things that I was unaware of. If you're aware that someone has seen this backward step, please get me in the discussion period. Yeah.
Okay, let's thank the speaker.
Thank you.
And move on with the session.